You are monitoring a jet engine's vibration data, a hospital's ICU telemetry, or a financial trading feed. A spike appears. Traditional anomaly detection models hand you a binary flag or a confidence score. But in high-stakes environments, a score isn't enough. You need to know exactly when the deviation started, how long it lasted, and why it doesn't belong. That's the gap this research closes. Vision language models have revolutionized chart understanding and visual reasoning. But when you drop a general-purpose VLM onto a time series plot, it struggles. Time series graphs don't have discrete objects or clear spatial boundaries. They're continuous streams of temporal patterns, periodicity, and subtle structural breaks. Out-of-the-box models either hallucinate boundaries, overflag normal fluctuations, or generate generic explanations that don't actually match the plot. The core bottleneck. Public benchmarks only provide interval labels. There's no natural language reasoning to supervise, which means you can't fine-tune a VLM to actually learn why a region is abnormal. The authors solved this by introducing VisAnomBench, a curated benchmark that pairs time series plots with high-quality, temporally grounded explanations. They didn't just scrape datasets. They took 4 public benchmarks, rendered segments as plots, and used multiple frontier VLMs to generate candidate reasoning traces. But they didn't blindly trust the first output. They built a composite reward function to quantitatively select the best supervision target. This reward weighs 4 specific dimensions: anomaly accuracy, which measures temporal overlap between predicted and ground truth intervals; visual groundedness, which checks if the reasoning explicitly references observable patterns like spikes or level shifts; axis awareness, which penalizes hallucinated timestamps or values that don't match the plot scale; and clarity, which ensures the reasoning is logically ordered and directly links visual observations to the final decision. By keeping only the highest reward candidate per series, they created a training set that teaches the model not just where anomalies are, but how to justify them visually and temporally. From this dataset, they trained VisAnomReasoner. It's built on QN2, 5VL, but instead of full fine-tuning, they use low-rank adaptation, or LoRA. This freezes the backbone and only updates about 1.13% of the parameters, keeping the model lightweight while preserving strong reasoning capacity. The model is supervised to output a strict parsable structure, an anomaly decision tag, precise index intervals, and a step-by-step reasoning trace. It's trained to map visual evidence directly to temporal boundaries. The results are stark. On the VisAnomBench test set, the 3 billion parameter variant pushes precision up by over 21 percentage points, and F1 by nearly 24 compared to the strongest baselines. The 7 billion variant improves precision by over 23 points. Why the massive gain? Most competing methods, including large frontier VLMs and specialized detectors, suffer from aggressive overflagging. They'll flag half the timeline as anomalous to catch the real event, which tanks precision and destroys boundary alignment. VisAnomReasoner's reasoning supervision forces it to discriminate between normal variants and true structural breaks. It drastically cuts false positives while actually improving recall. The ablation studies prove that the explanations aren't just decorative. When they fine-tuned the model to predict intervals only, precision jumped, but recall plateaued. Adding the structured reasoning traces pushed both metrics up. The model learns a causal chain, identify the baseline and axis scale, locate the deviation, map it to precise temporal indices, and conclude. This structured reasoning also improves temporal boundary alignment, measured by the overlap score, which penalizes both undercoverage and overextension. In plain terms, the model learns to draw tighter, more accurate boxes around the actual anomalous region. Cross-benchmark evaluation on TSBADU confirms this isn't memorization. VisAnomReasoner generalizes to unseen time series characteristics, improving standard precision and F1 by roughly 10 points, and affiliation metrics by nearly 19 points. Affiliation metrics are crucial here because they evaluate event-level detection with tolerance for minor boundary shifts, which is how real-world operators actually use these systems. Inference is also highly efficient. The model processes rendered plots, not raw token sequences, so runtime stays around 16 seconds per series and doesn't scale with sequence length. It's significantly faster than pipeline-based VLM approaches and avoids the context window limits that break text encoding methods. There are limitations, and the authors are transparent about them. The current implementation is strictly univariate, reasoning over single-channel plots. Performance also depends on visualization quality. If the plot is too zoomed in or out to expose the pattern, the model's reasoning will suffer. This is a known trade-off of vision-grounded approaches. Future work will likely explore multi-resolution plotting, reinforcement learning for interval optimization, and extension to multivariate signals. But the core insight is clear. Anomaly detection is shifting from scalar scoring to grounded reasoning. By coupling reward-guided data curation with parameter-efficient fine-tuning, VisAnomReasoner demonstrates that smaller, specialized models can outperform much larger, general-purpose ones when they're explicitly taught to reason over temporal evidence. For anyone working in industrial monitoring, healthcare diagnostics, or cybersecurity, interpretable, visually grounded anomaly detection is no longer a nice-to-have. It's a deployment requirement. Check out the paper and the code. If you're building or evaluating time series anomaly systems, I'd love to hear how you're handling explainability and boundary localization in your pipelines. Drop your thoughts in the comments, and I'll see you in the next one.